Today's class, we will do the hybrid system, a 2D hopper. A 2D hopper because it will only move in 2 dimensions in the XC plane. So again, go to tiny.cc MuJoCo, download template underscore pendulum.zip, and do the usual thing. Rename it to hopper, make those 3 changes, and then in the shell, navigate to the folder hopper and then type run Unix or run win to see if you can get the code for the pendulum running. So if it runs fine, you should see an inverted pendulum standing in front of you. Let me just do that. Unzip hopper, view this file. So let's go to main.c. Right here on line 28, change this to hopper. Okay, and we'll also change the name of the XML to hopper. We'll make those 2 changes. And this will be hopper. Next, we'll open makefile. Uncomment the right flags for the operating system. Change the root to hopper. Close this. Open run Unix or run win, depending on your OS. Change that to hopper. And I'm going to open the hopper.xml. Okay, now let's go to the shell and get to this folder hopper and then run the Unix file for Mac. Okay, so that's the pendulum, which we had created a few lectures back, and that works fine. So everything works. Okay, so now what I'm going to do is the first step is to create the model for the hopper. Okay, our model for the hopper would be something like this. There is, well, this on the left side, you see the model, the world frame, torso, that's the body, leg is another body, foot is a body. So everything in the red is a body. Everything in blue is a joint. So translation XZ, hip joint, and knee joint. So we're going to put a torso, but a torso is not going to be a stick, but it's going to be a sphere, okay, a point mass body. And then that would basically move in the free to move in the X and Z directions. So that's a sliding joint. And that body will connect a leg using a hip joint denoted by Q1. And that would have a mass inertia. Then we'll connect a foot to the leg using a sliding joint. And that you can think of that like a knee. One of the purpose of the knee joint in a human is to allow for ground clearance, and that's what this will do in some cases. And then we'll actually join the leg to the foot with this massless bar, which you see behind the arrow. Okay, and that massless bar will not really affect anything. It's just to make the visualization look good. Okay, so I'm going to go ahead and do this work in the XML, and I think that's best to work with the simulate executable and see how the changes manifest in that simulate executable when I change the hopper.xml file. So let's do it that way. So I need to navigate 2 levels down, and then go to bin, and then simulate. Let's drop the hopper And you can see the pendulum. Let's first show the join. So rendering join, and you can see that the pendulum is in the vertically up position. So I'm going to modify that so it is vertically down in the downward direction. So that's how I want the hopper to be. So this 180 should change to 0. Then we can reload. Okay, so it went up. Okay, now we have two options. We could start building the top part or the bottom part. It's really up to you. I mean, I'm thinking let's build the top part of the hopper. So we'll basically put the torso first and then work that to that and then get to the foot. Okay, so for the torso, we know that this particular body is the cylinder here shown in green, and we want that to be called the leg. So let me just call it to begin with as the leg. So body name, we'll give it a name. So name equals torso. And then perhaps change the joint. That joint would be so it's a pin joint and it helps to move back and forth. That's the hip joint. So we call that hip. Okay. Is there anything else? I think that's good enough. Okay, now I have to add another body, the torso, and that torso, the body torso is connected to the world frame, right? So I need to create the body tag here and then name it. Oh, sorry, this should be leg, my bad. The leg is the green one. So this body should be the torso. Also. And for now, let me just create it like so. And then I need to tell it that the body is the ending bracket. So I can maybe just indent this one level so that it's from the indentation, it looks like the leg is a part of the torso. So the leg, the body is defined within world, and then the leg is part of torso, which is what we want. Okay, now let's define those two joints, which are the X and Z motion, right? So joint name equals this, let's call that the X joint, and that really doesn't have any meaning here. It just helps us to move in the X direction. The type is slide. And see, okay, now we need to deal with the position. So let me, in fact, even define, actually only need to define the position of this. So when I said pause 002, it basically set the position of the center of mass of the leg at 002, which is along the z-axis 2 units. What I'm going to do is, instead of that, I'm going to put this one at 002, so that torso is on the z-axis at coordinate 2. And this I'll just for now make it 0 and see what happens. And then accordingly, depending on the animation in the visualization, I'll change it. And then I need to finish this joint. Let's see. I need to define the position. Let me just define for now 0, 0, 0. And then I need to define an axis, and that has to be 1, 0, 0, signifying motion along the x-axis. End it. Okay, so let's reload this. There's an error. Oh, there is I have a actuator specified. So let me just comment that out. I'll work on that. Let's load. There's another error. Okay, mass inertia of moving bodies must be positive. So you cannot define no mass or inertia because then it treats mass to be 0. So I'm missing that somewhere. So I think it's well, there is a way to define mass using inertial tag. I'm skipping that, but I've done it in one of the lectures. I'm going to use this tag, the geometry, to define the mass. I'm just going to copy this right here. Okay, and this one will be my torso, so it will be a sphere. And I need to define with one parameter. So let's call that 0.1 for the radius of the sphere, and then let the color be as it is. Mass is 1. I think this should work. Should reload. Okay, so that's the x-axis, and then the mass is sitting right right in the middle. Okay, so the thing is, I've first specified the position of the torso. That is right. It's just the issue is that since I've specified 0, 0, 0 for the position, it put the center of mass of the leg, which is this cylinder right in the middle. So what I need to do is I need to move this cylinder down, right? And how down? Well, I need to move it by, this cylinder is of length 1 meter. So I need to move it 0.5 meters down. So I think it would be negative 0.5 because upwards is positive. So I think if I put minus 0.5, it should be done. Okay, now it moved. It moved down and this thing is at 0.02. Okay, I want to change this color. So let me just change the color of the torso to gray. So the gray is, I think, point like this. Here, 0.9. 9. Then reload. And then if you want to check the joint in the x-axis, just change the gravity along the x-axis, and then so reload, and it will fly in along the x-axis, so it works. Okay, now let's introduce the joint along the z-axis. This is easy. Just copy this, paste it. Let's call it z, slide, same position, and this is along 0, 0, 1. So reload. And now it falls down because there's no gravity in the x, but there's gravity pointing down. So it's my best interest. I need to probably work with no gravity to build this model and then turn the gravity on. So reload. Now nothing moves because gravity is turned off. So you can see that I've created 3 joints, 2 for sliding and 1 for rotation. If you want to check that, you may as well rotate the joint by I get 30 degrees. So you can rotate the leg by 30 degrees. And then you can see it comes off. So when it rotates, basically rotates the center of mass by 30 degrees. And that's why you don't see the joint quite at the torso. So you need to, it's a little bit, it's actually better to rotate it using the code main.c by just changing the initial angle to 30. So this is not a good idea because it just removes the leg from the torso. So let's not do that, but it's there. You can see from the figure. So reload. Okay, so we've got 3 joints. Now what we're missing is the foot. Okay, so let's create the foot right below. And and I want to connect the foot to the leg by some cylinder of 0 mass. Okay, but let me create the foot down here. So let's take the code for the torso and paste it there because we'll be using a sphere for that. So body name, we'll take this and paste it within the leg because the foot sits within the leg. So we'll call it a foot. For now, let's define 0, 0, 0. And then we need to specify a joint. The joint is a pin joint, so it's a sliding joint. So we can take this one because it's going to be sliding joint along the z-axis. Okay, and then I need to call it something. So let me call it, I think I specified it as knee joint. Slide 0, 0 is fine, and then 0, 0, 1 is good. And let's just reload this. I think it will not work because I did not end the body tag. So now it should work. There's a code problem. Let's see what's the problems. Mass inertia is same issue. I need to specify the geometry. So let's choose that to be a sphere. So I'm copying this from the torso because that's the easiest to modify. A sphere of size, let me make that slightly smaller. Let's say 0.25. And let this be so. And I want to make the foot a lot lighter than the leg and the mass. So 10 times lighter, so mass is 0.1. So now it should work. So reload. Okay, so you cannot see it because it's inside this green thing. So what we can do is to see it, let's just change the diameter of the cylinder. Okay, and now maybe you can see it. There it is. So it's sitting right in the middle, and you can see the axis of the sliding joint is upward. So I need to do two things. One is move that axis down, which means that I need to change this to -1. Okay, so it'll go down. You can check it. See, it's down. And the second thing I want to do is I want to move this foot. Well, let's first move it down the tip. So we know that this distance is 0.5. And since you're moving in the negative z direction, I think we should put -0.5. So let's change this position to -0.5. Okay, that looks good. Now, what I want to do here is I want to basically have a sort of a shank or something between the foot and the leg. Again, that will help me to go up and down when I, for example, for ground clearance. So I want to move it slightly down by, let's say 0.25 meters. So instead of -0.5, let's go 0.75. Okay, now it moved down. So this is going to be my foot position. And then I need to connect the end of the leg to the foot using a sphere, a cylinder of the right length, which is in this case, the length is going to be 0.25 because I moved it down by 0.25. And I need it to be, what else do I need? I need it to be of mass 0 because I don't want mass on that. So I'm going to create another geometry, okay, in the same place where the body foot is defined. So take the code from the cylinder because it's going to be a cylinder, paste it right above sphere, and let's make it, okay, let's make it blue. So blue would be 0.9. And then I want to make it massless. Okay, this is of length 0.5. Clearly, I don't want it to be 0.05. The length should be 0.25, but I need to define half the length. So I need to define it as 0.125, which is half of 0.25. Okay, let's see what happens when we reload. Okay, you can, well, let me get rid of this joint because it's interfering. So you can see it's created right at the foot, the center, and then it is, it's not how I want it. I want it to move up by 0.125. So in order to do that, I have to move the position of the cylinder. And so I'm going to define a new thing, the position. Okay, since I need to move the center of mass of the cylinder upwards by 0.125, I'll just have to say 0.125 plus for upwards. And now reload. Okay, it looks good. Okay, it's a good connection. Okay, and then now we can turn the joints on. Okay, the joint is probably here. I mean, here it doesn't really make a difference. You can define it the way it is in the foot, but I think I'm more comfortable if it's right at the tip of the blue where the blue starts. So I need to move it up by 0.25. So the sliding joint, I need to move so it's upwards, so it should be positive. So reload. Okay, I think it's right where I want it. Okay, so that looks like I have my model. I'm just going to clean up a few things. I'm going to increase the size of the leg back to what it was. Where is the leg? The leg. And then the size is, I think 0.1. It's too big. I think it was 0.05. Okay, that looks good. The blue can let be as it is. This ball should probably be I'm gonna make it slightly bigger. It's barely visible. 0.05, and if we change the color, we'll change some random number there. Yeah. Looks like yellow. Okay, I think that's about it. Now, one thing you might wonder, how I could get away by defining cylinder with a mass of 0. If I specify a mass of 0, it should give an error. It turns out it won't give an error here because here there are two geometries. There's a cylinder and a sphere attached to this joint. And as long as one of them is non-zero, it's fine. So for example, if I comment this out and then reload it, it'll give me an error. So so mass inertia should be positive. So if you want it to go away, I need to even specify at least some small non-zero value. So if I do reload, then it's hard to see if it worked or not. But what we can do is keep that on the right side and do reload. And then it didn't look like it printed anything, so it's fine. So let's get this back to 0. And then uncomment this. And now reload. Okay, so what is there? There was hopefully no error. And I'm done with specifying the geometry. Now, I also need actuators. So let's see. Pull my slideshow. Okay, so in this case, I cannot control the X and Z motion because it's free to move. The only places where I have an actuator is the hip joint. I can have the hip move back and forth, and I can have an actuator, the knee joint, and that can be a sliding joint, right? So what I'm going to do is, well, there are two ways to do it. Well, I could specify a motor torque and then do, I'm planning to do position velocity control or PD control, and I can do a position derivative control using that. Or I could just specify a P servo, V servo on the hip joint, and same thing for knee joint, and then change the gains. It's both those methods are equal. I'm just decided I'm going to go with a position and a velocity servo. So I'm going to define a PV servo for this joint, hip joint, and a PV servo for knee joint. And then I think it should be done with the XML. Let's define it in the code. So we already have this from last time. I uncommented it. I don't want a torque actuator, so I'll delete that. Okay. Now, first actuator is going to be on the hip, this joint, and that's hip. Let me call that P hip, P hip, or sorry, P servo hip, V servo hip, and then arbitrarily define these KP and KV as 100 and 10. Okay, let's reload. And if everything worked fine, then you should see those controls here, right? You can, for example, change this. And it's floating because of the way it's a reaction torque, which made it go fine there, gravity 0. Okay, let's copy that. This is the knee. And I call it joint is knee, which is right here. And then let that KP, KV be the same. So when you reload, everything was good, then you should see 4 actuators, PV for hip, PV for knee. Okay, so I think I'm all set to proceed to the next step. Now I'm going to go to the main file and then modify things there. Before we quit this, I think it might be a good idea to actually print the model. I'll need that later on. So if you go to print model, just click it once, it'll create the model in the bin folder, and you'll have to manually take that model from the bin folder. It'll be called mjmodel.txt, and then paste it wherever you want. So let's go to the bin folder. It will be this one. Okay, it was created at just now. And then if you see this in Q4, looks right. Okay, let's copy this. Then let's go to hopper, paste it. So it's ready reference. Okay, so we have that. Now let's quit this simulator. I don't think we'll need it anymore. Then navigate back to one level down, then go to my project. And then hopper. Then run Unix. Okay, so gravity is disabled, so nothing is moving, which is what I would expect. It's closed. Okay, so let's turn gravity on. Okay, gravity is minus 9.81. Okay, and now run this. So it just penetrated the floor, and that's because I had disabled contact. So let's go there, here, and then enable contact. Okay, now hopefully it will not penetrate the floor. Okay, now it just stopped, right? It just stopped because I have a PD controller or KPKV, and that's why it stopped. Now, one way to get this to hop in place is to simulate a spring between the floor and the foot. And what we can do is we can just set the KV to 0 and run this. Okay, so it stopped, and I think that it's vibrating because it's like a spring, but it doesn't have enough gain. So let's change the gain. That's equivalent to having a spring of stiffness 1000. Okay, so there it is. So it's hopping. We already got it to hop without doing much. Let me just increase the time. Let's say 10, or let's say 15, and then just observe it hopping. Okay, so you can see that it hops, but then the foot is vibrating like crazy, and that's because it's just a position control. It's not trying to set the velocity to 0. It just wobbles back and forth, and it's also see that sort of gaining energy. Okay, so we got it working, but we want to do things like not make it wobble when it's in the air. We also want it to move forward, not just hop in place. So we need to now work with the main.c in order to do those things. Okay, so what I'm going to do is, first of all, I'm going to, so before I get to, so my goal is to use a state machine to do all the control. But before I get to the state machine, I want to essentially write some code to set the controller gains in the main.c instead of relying on the XML. Okay, so this is sort of like build up for the next part, as you see. So what I'm going to do is I'm going to set these gains to 0 because I don't want to set them through the XML. I want to set them through code. Okay, so if you run this now, it'll probably not, it'll just fall, right? Okay, that's good. Now let's go to main.c. Right here, I will initialize those gains. So if I go to init controller, this is the function which is called the very first time at time t equals 0. And I need to initialize the position velocity controllers here. So this is sort of a review of what we've done in the past. I've already wrote down the code, and this was developed in one of the classes to basically set the position and velocity gain depending on the actuator numbers. I'm going to use this code again. So this one helps me to set the position servo. So we copy that here. I need to pass the model. I need to pass the actuator number, and I'll tell you what that is in a bit. I'll define actuator number to be an integer first, and then I need to specify which actuator this is. So in this case, since I have 4 actuators, basically 0 is the P servo hip, 1 is V servo hip, and so on. So this should be 0. And then I need to set the gain. And remember, I set that to 100. So I'm just going to set it this way. Okay, so that sets the position servo. So next one is a v servo. So I need to call, instead of set position servo, I need to call set velocity servo. And the first two arguments are the same. It's only the gain kv I need to set. So let me set the velocity servo. And then that would be actuator plus 1. And then I need that to be 10. So this is the servo hip, v servo hip. Okay, then I just copy this, and that'll be 2, 3, and the same one. So all set. I think this will work. So it should give me the same results I got when I put those gains in XML. So I'm missing, okay, it's called actuator. Let me just call that number. It stopped. I should have changed this to 1000 and 0 just to get what I got earlier. Successful hopping in place. Okay, that works. Okay, let me kill this. Okay, so I've said this, and this is how I will modify the controllers in my state machine. Okay, so let's see how to build a state machine. So this is by far the most complicated state machine we'll see, but it's not that hard either. Okay, so what I'm going to do is my state machine. So first of all, I start this hopper in the flight phase, right? I just drop it with 0 velocity. So I'll call the phase when it is dropped and going downwards as air1. So finite state machine called FSM air1. Then when it is touching the ground, the foot is touching the ground, it is compressing. And so the velocity of the torso is downwards. That will be called stance 1. And then when it is going upwards, it'll be called stance 2. And then when it's going upwards, it will be air 2. And then after it finishes air 2, it will start going downwards when the velocity goes to 0, and then I'll go back to air 1. So the way this goes is air 1 goes to stance 1, then stance 2, and air 2, and so on. Now, that just is the states. I need to define the transitions, right? How do I transition from these states? So, and this is sort of obvious from the way I've specified the state machine. If you're in air 1, your velocity of the torso is downwards, and you want to transition to stance 1, then you only need to check if the foot touches the ground. So I need to check the height of the foot. So as long as the height of the foot is the right place, then that is the contact point at 0. In fact, here the height is not 0, but it is going to be the radius of the sphere. It's going to be whatever I defined it to be the radius. So that will be when I would transition to stance 1. Then between stance 1 and stance 2, the difference between these two is that the velocity of the torso is going from downwards to upwards. So I'll just check the velocity of the torso. If it is upwards, I'll transition to stance 2. Then I will check the foot position. And if it is not equal to the radius, it's greater than the radius because upwards is positive, I will know that the foot left the ground and transition to air 2. And then again, if you see the difference between the hopper on the right and hopper on the extreme left, the difference is the velocity of the torso. So if the velocity of the torso is changing from air 2 to air 1, it's changing from up to down, I just need to check the velocity to be less than 0. And so I need to program all those reds, okay? In order to program the reds, I need to first figure out how to access those reds from MuJoCo. And MuJoCo will give me, for example, the position of the foot, the velocity of the torso, and so on. So I'm going to do two things here. I'm going to first create the state machine with all the states, and then I will work on the transitions and get this all figured out. Okay, and then we'll go to the next part, which is the actions, that is what you do within the state. So let's get started there. So all the state machine variables should be defined outside the code as global variables. So let me call that FSM is my variable, which will keep track of the states. I'm going to define FSM air 1 call it 0. Define FSM stance 1, that's 1. Define stance 2, 2. Define FSM air 2. Okay. So once I've defined the states, I need to initialize the FSM. The place to do that would be in the init controller. So go to init controller, initialize the FSM to FSM air 1. So we've initialized the state machine. Now we have defined, well, so let's go into this slideshow. We have finished this part. We've defined the states. Now let's go and define the transitions. So before I define the transitions, I need to get these positions. I need to get the position of the foot, and I need to get the velocity of the torso. So let's get that thing first. Once we get that thing, we can then program the transitions. So get data for transitions. I'm going to just inspect the values I get for the position, because I need a trigger for the position of the foot. Okay, so how do I get the foot position? Now, this is where you can use the XML file. Sorry, the TXT file. So if you look at the TXT file, the model file, then I'm going to use a variable called expose. Show where it is. Go to MuJoCo API reference. Expose. So expose is the Cartesian position of the body frame. Okay, so here I'm looking for the position of the foot, right? And so I need to know which body it is, because the variable is n body times 3. So every body will have three numbers associated with the expose, which will be the x, y, and z coordinates in the global frame. So here, body 0 is world, body 1 is torso, body 2 is leg, body 3 is foot. This is what I want. So it's going to be it'll be 3 times body number, so 3 times 3. So the 9th element would be the x position, the 10th element would be the y position, and the 12th, 9, 10, 11th position would be the z position. Okay, so I'll show you an easy way to write this. So if you know the body number, it's the third one, and if you know that it is n body times 3, then this is how you would write this in a meaningful way. Int body number. So here body number is 3, and I want to access the position. So it'd be d expose 3 times body, because there are each body will save 3 numbers x, y, z. So I should do 0 for x, 1 for y, 2 for z, and then I'm just going to print this. So printf foot position. Okay, so that should give me the foot position. I also need the velocity of the torso, right? So now, like expose, it would be nice if there was a v pose that gives you the velocity. Turns out there is no v pose. There's no function, no variable gives you the velocity. So one way to find the velocity is to define a sensor. So if you go here, define a sensor, and that sensor would be the frame velocity, then you can get the velocity of the torso. But what I'm going to do is I'm going to use a simpler way to get the velocity. I know that in my model, which is here, I have set the z position, the z variable could correspond to the velocity of the torso in the upward direction. So all I need to do is get access to the velocity associated with the z variable, and that is stored in qvel. So if you look at the documentation, it is right here. This is the velocity associated with the degree of freedom. So in this case, I'm looking at the velocity of the second variable, or the by indices it will be number 1 because indices start from 0. So if you go here, you can also find it. Body 0. I want to look at joints. So joint 0 is x, joint 1 is z, and so I'm looking at the velocity. So I need to do qval 1 to get the velocity in the z direction for the torso. So let me first just print it to understand if what I'm getting is right or wrong. So z velocity torso is %f. So I said it was d qval 1. Then I'm just going to do printf just to show it's a new line. Okay. So I'll run this and see what I get for the position. So let's put it in the background. Okay, so you can see that the foot position, for example, since it's bouncing in the z direction, you don't see the xy changing, and then the z velocity changing. Now, I know for sure that, so going back here, I know for sure that the velocity of the torso is going to change from positive to negative. What I'm unsure about is the position of the foot. What constitutes the foot touching the ground? And that's what I'm going to find now using this code. So you can see that this is hopping back and forth and really hard for me to visualize what exactly is the position of the foot when it's contacting the ground. So what I'm going to do is I'm going to make it such that the gain I'm going to change the gain of the knee servo to, let me just change it to 100. And now run this. So when I change it to 100, what I see is it actually gets stuck to the ground. And now I can just read it off, right? You can see this. It's 0.4748. So it looks like it's about less than 0.05. I can use 0.05 to be the trigger for the foot position, for the foot to be grounded. And the reason it's not 0 and 0.05 is because I've defined the sphere with a certain radius. Okay, so my trigger is 0.05. Okay, so that's all I need. So I'm going to now go ahead and set these transitions based on this diagram. So let's keep it to the side. Let me open the XML. Okay, and go right here and then set all transitions. So remember I'm starting from air1. So if FSM equals to FSM air1, and so I'm now trying to program the transition from air1 to stance 1, and for that I need to get the position, the z position of the foot. So I need this variable. So we call that double z foot equals that, and of course I need to specify the body number. I can comment this out. I don't need this anymore. Okay, so body number is 3. I get the z foot position, and if the z foot, and I saw that the transition value is 0.048, so 0.05. So if it is less than 0.05, I'm sure that the foot has contacted the ground. So z foot less than 0.05. I say FSM should transition to FSM stance 1. Okay, so transition. Okay, next let's go to, let's say we want to program the transition from stance 1 to stance 2. So that I do is FSM equal to FSM stance 1, and now I need the velocity of the torso. So let me create that variable VZ torso, and that, as I said, is this variable. Let's take that. And now if I know that VZ, so if I want to go from stance 1 to stance 2, then the trigger is that the velocity of the torso should go from negative downwards to upwards. So as long as VZ torso is greater than 0, I have the transition. So greater than 0. Now I can say FSM equals, let's take stance 1, FSM stance 2. keep going. Next, I'm doing the transition from stance to air 2. So FSM equals FSM stance 2. And now, just like Z foot is less than 0.05 signifies touching. If it is greater than 0.05 signifies takeoff. So Z foot greater than 0.05. Then FSM equal to FSM air 2. And then the last transition I'm missing is air 2 to air 1, and that's when the velocity of the torso is less than 0, that is going from upwards to downwards. Let me type that. If FSM equal to FSM air 2 and VZ torso less than 0, then FSM equals FSM air 1, and that's it. And now once it's air 1, it'll transition to air stance 1 based on this condition. So it basically is an infinite loop. Okay, so how do I check this? Well, here's one easy way to check. Printf. I just wanted to print FSM stance 1. Stance 2. Air 2. Air 1. So it's just saying that if everything works right, if it's taking a step that is bouncing off back and forth in there and going down, then it should basically print this each line one at a time, right? And so we do this. We also want to ensure that it actually bounces off the ground. So in the init control, I'm going to set this back to 1000, and I know that worked. So let's see what we get now. So we run this, we'll bounce back and forth. Okay, and then if you look at this, you can see it's transitioning stance 1, stance 2, air 1, just like what we expected. So these transitions are going through all right. Okay. It's okay. We got that. Now, I think it's a good idea to keep track of step numbers, right? So every time it goes from air 1 back to air 1, that's one you just increment the step number. So I'm just going to keep track of steps just for my information to see how many steps it takes. So let me just define a global variable step number. Initialize the step number to 0 in init controller. And then, just increment it every time I reach FSM air. Step number plus equal to 1. And then if you want, you can just print it. %d step number equals %d line step. Let's see now what happens. Okay, so it's here. Step 1, step 2, step 3, and so on. Okay, it's good. Okay, so I'm just going to comment this printfs. So I only see the step numbers. I know that it's transitioning, the steps are increasing. That's how I know it doesn't fall. Okay, now it'll only print the step number. Okay, so we've got to the point where we have created the transitions. Okay, so the next step is to actually write the actions. Okay, so now what I'm going to do is write the actions, what happens in the states. And the goal here is to ensure that that weird wobbling you see in the foot doesn't really exist when it's in the air. And so what I thought of doing here is the following. Remember, we have a position velocity servo on both joints, right? So what I'm going to do is I'm going to set all the servos to have a 0 reference. So everything at 0. So 0 for this. And I'm not going to play here with the hip servo at all. I'm only going to play with the knee servo. And the reason I'm playing with the knee servo is because I only want to think how to do height control. So this is actually incorrect. This is, yeah, so my bad. This is right. Knee joint is used for height control. So the goal here is, what I'll do is I'll set a spring. So let's say the spring constant is 1000 when it's compressing. If I suddenly change the spring constant to a bigger value, greater than 1000, so 1000 to, let's say, 12 1200, then it'll actually bounce off much higher, right? Because the spring constant has changed in the retraction phase. So what I'll do is I'll basically set a high gain, only a P servo when it's in touchdown. That way I can get the spring action. But once it's in the air, I'll set the velocity gain on. And what that will do is it'll damp out the oscillation. So it'll be stuck at a position. It won't really wobble back and forth. So this is the logic which does it. So I set a position controller by turning the gains for P and V. In this stance one, I only set the P servo stance, and then PV control in the flight phase. And I do this only for the knee joint, okay, because I want to do height control. So let's set this up. Okay, all actions. So this is simple. This is just say FSM equals to FSM air1. What do you do? And so on for each phase. Okay, so for the first phase, air1, I want to set a PV servo. So what I do is I just take this code for, and remember I'm doing knee control. So it's going to be, these two are hip, these two are knee. I should write this as knee and knee. Take this and paste it here. So as I said, I need to set some position velocity control. So I'm setting it to my default values of 110. That will ensure that it's a PD control. Okay, let's copy this. Let's do stance one. So in stance one, I only want to do a P control, no V. So I'll set this gain to 0. And this one I want to set it to 1000, right? So we just set it to 1000. Copy it again, stance 2. So I want to set this to, let me just set it to 1000 now, and then I can change it. So increasing it, it will make it basically fly off much higher. And then that should be 0. And then air 2. So again, I go revert back to my PV control. Okay, so now my claim is if this works right, and you will see that it is not wobbling, it's in there. That's the only change I did by specifying the state machine. So here we go. Then error, I did not specify actuator. Let's just specify that right in the beginning. Like here, maybe int actuator number. Oh, I missed the name. So it's FSM stance. 1, 2, 3. It's 3 errors. Okay, fix this. Okay, now you can see that it is not wobbling when it's in there. The foot is not wobbling. Okay, now let's try to do height control. If you want to do height control, then all you do is change the gain here. So you want a higher gain in stance 2. So I don't know, let's try 1200. Okay, so it's jumping very high, and each time it's actually building up velocity because the gain is just 1200, but it just amplifies the velocity with which it landed. Okay, so we don't quite want that, so let's just change it to 1000. Okay, so we figured that out. Now let's do the next part, which is we wanted to move forward. So the final part is to get the hopper to move forward. So this is what is known as the velocity control, the forward speed control. Here, what we do is the following. We only control the hip joint, okay? So not the knee joint. And what we'll do is we'll basically specify, so right now it's set to be vertically downwards. That is the angle of the leg. So it's 0, it's going to be 0. When it is in stance 2, that is when the torso is moving up, I'm just going to change the position of the hip to be minus 0.2. And what that minus 0.2 does is basically torques the leg. So it sort of gives a kickback. And that kickback will make it go forward. And then because the kickback, it's going to be lean in the forward direction by minus 0.2. You want to get it back to a position of 0 in L2, otherwise it'll actually be inclined at an angle of 0.2, as you'll see. And then it'll actually fall down. So I'll first, just set it to minus 0.2 and show you what happens. And then I'll set that to the right value, which is 0. So the idea here is to just give that kickback instance to, that's all I'm doing. And with the the hip actuator. So let's copy the code for the hip actuator from the init functions. This is the one. Okay, it's well, actually I don't need to change this gains. The gains are not changing, as I said here. All servos and gains are fixed. I only need to change the commands or the controls. So the controls for the position servo. So that would be what variable is called CTRL. So let's go SMR. Here it is. So I need to set DCTRL. And since this is the position of the first actuator, which is numbered 0, so I need to just change that 0 to, well, it's set to 0. I'm just writing 0 again. You know what? Let me not write it there. I'm just change it here. So I need to change it at the stance 2. So let's go to stance 2 and then change that to minus 0.2 and see what happens. Okay, so you see it started leaning and then it just kept leaning there and then. It's interesting. This is, what do you get? Why did it fall? So I need to set that 0. I think that's about it. I don't need anything more than that. So you can see it's going forward, keeps going. Actually, eventually, I think it loses energy and falls. A couple of things I need to probably do. I need to increase the size of the RAM for sure. And I think I want to make this camera go with the move with the hopper. So I'm going to do those changes first. So let's just increase the time first. Let's make it 30. Okay, that's first thing. Secondly, let me increase the ramp size. The ramp is right now 0.5 in the sorry here 1 in the X, 1 in the Y. This robot is hopping in the X direction, so I only need to change this. I can make it like 100. So it's going to be 100 units in the X direction. And what else I say? I wanted to make this camera move. Well, before I change it, let's just see what it looks like now. Okay. Okay, red carpet. So it's losing energy and it's also going out of view. So I'm going to just make the camera move in the X direction. So I'm going to stop it. So I think eventually falls. Yeah, there it stopped. So let's go here and then right before rendering. Yeah, right before rendering in the main loop. Right here. I need to change the cam.lookAt. That will be the X position. So that, and then I need to decide whom to follow. Let's say that we want to follow we can just follow the X position. So Q pause 0 will do it. That's following the X degree of freedom, which is basically the velocity of the torso, so the position of the torso, same as that. Run. Okay, so now you can see the camera is following the robot. And then it damps out. Okay, so to prevent it from damping, I need to inject some energy. So let's inject some energy. It actually took 28 steps. So go to main.c, go to where I've defined the actions. So it's 1,000. Let me just change it to 1,100. You can change the view if you want. I think it's gaining height, maybe not. Yeah, you can always decrease that 1,100 to something 1050 and then see what happens. I think it's gaining height. Let's change it to maybe this is slightly better. It's a bit dark. I can actually change this background to be a little bit lighter, not so dark. Okay, I'll show you that to you in a bit. So it looks like this is okay. It's went 31 steps. Stop. Okay, so we can change the lighting. This is something we can change in the XML. So go to the XML reference. And then let's do. So we want to search for light. It should be in. So right now, if you look at my hopper, you'll see that it's defined in the body, world body. So I need to search it here. There should be a light, that light. So light, and you can you can actually track something, track COM, track target body, and so on. So let's just track the. We want to track the torso. So let's just track the torso. Just change this. So light remains same. I say mode equals track target body. So track target body. And my target is torso. You can see there's a faint light on the torso. That's the one which is tracking. So it's the torso is in the spotlight, and then it's moving on the red carpet. Okay, now if you want the whole thing to be brighter, then there's a way to do it to scale this. There is a visual tag somewhere here, visual. And that visual you can actually set visual quality, visual headlight. That was what I was looking for. So you can set the headlight to be something different. That will change the whole scene to be more brighter. So I'm going to use something, let's say ambient. Okay, so this goes in its own tag. Let's find here visual, and then I need to end it visual, and then I need to define headlight. Now is end it. Okay, now I need to define that to be ambient, and then I can specify whatever values I want. Ambient equals 0.5, 5, 5, and then run this. Okay, much brighter. And you can play with the value.